Okay, hi everybody. It's Andrea Howard here from Carleton University.
And Oscar here from the University of Washington.
And we're talking simulation today because I think we both noticed that a lot of people have become aware that, especially when it comes to things like power analysis, we increasingly need to be able to do things like simulate our model before we can figure out whether our model is properly powered or what elements of our model are properly powered. And I just did a Twitter poll on this the other day. Most people do not know. Do not know how to simulate things.
I kind of feel it's one of those things like, you hear about it, you know it exists, but sort of like that's the extent of your relationship with computer simulations.
Right. So you and I thought, okay, well, let's spend one of our episodes just kind of walking through how simulation works. And Oscar has been working a little bit on setting up basically an intro to simulation for those of us that don't really know what that's all about and exactly how something works in a simulation. So you're going to share your screen with us.
Let me share my screen.
We will sort of try and talk through this problem together.
Yeah, no, so it's a very, very basic thing. And as you can see, like I'm being very retro because I'm old. So this is what my screen looked like when R started. Like, so none of the fancy smancies of the, what's the thing, the Tidyverses, the R Studios, none of that existed when I was a graduate student. But this works. And so this is a very basic introduction, and I just want to emphasize, like, there might be a few things that perhaps people who are savvier at these might consider, like, oh, no, this is so inefficient. He's using a for loop. Oh, this is so inefficient. He has to like create his own way to save your results. It's like, yes, we are aware of this. Don't add me. But we want to emphasize really just like the back to basics is like step by step, little by little. So pretty much like, I guess the first line, sorry?
So, okay, so what am I looking at here? So I think we're going to operate under the assumption that people watching this have had some exposure to R software. So you've got a library statement. So we're going to load up the ggplot package for making some plots, and we're going to load up the power package so that we can do a couple of quick power tests at some point in this. What's this third thing? Options, SciPen.
This is very Oscar-like. You could remove these and nothing would change. It's just like, I don't know, scientific notation bothers me.
Okay.
So these forces are to write out all the decimals, and entirely stylistic. Like nothing would change if you were to remove it, but like it just
That's one of your things. Okay.
So we declare
starter.
them.
Yeah. Okay.
And I guess this would be like from the very basic steps. Our statistical computer programming has all the bells and whistles to all kinds of interesting things. And well, for us, like the first thing to start is learning how we can create data that looks the way that we want it to look. So the most basic thing that we perhaps could see is normally distributed random variables. Yes, that looks ugly and awful and probably not the way that we would want to see it. But if we do this kind of thing, it's like, okay, give me 10,000 randomly distributed variables, variates that have a population mean of 0 and a standard deviation of 1. And I'm doing this data frame function here for people who are a little bit unfamiliar, just to make sure that it's, it is in the right format for ggplot to plot it. And if you were to do that, unfortunately, and you check the name of your new data set, it uses this ugliness, which of course we get rid of that with defining the column name of A as X.
Yeah. So you've just basically made a variable containing 10,000 observations, and those values kind of have a variety of negative and positive values, with an average of 0, a standard deviation of 1, and the head statement here is just to show the first 6 in that variable.
That variable, exactly. Yep. And if you were to like plot them, just to, because, you know, they kind of say like, oh, okay, it's nice, it's well shaped. You can see if you were to sort of like do the mean of your data of like, wait.
Let's see, what do you call it? You called it something new now.
Exactly.
Yeah.
Well, like, I mean, I'm
Right.
using the dollar sign to extract the data itself is one of the things of working with, I guess, data frames. Just like you sort of like need to tell it what the column the data is, but just empirically, well, you have a value that's not zero, because it shouldn't be zero. You need to have a little bit of variability, otherwise it's not like a Monte Carlo simulation. And the same thing with the standard deviation. Well,
Yeah,
it's close to one, but it's not exactly one.
Yeah. Okay. So, so basically what you've done here is ask the computer to make up 10,000 values. And then we just put that in a variable, right? So this literally is made it up from scratch. And you've just plotted a histogram of them. And that histogram has the properties of the distribution that you've asked for, and that
we would expect
fundamentally is what simulating is, right? So you've given some properties. You've said, well, this, it's frequentist, so it means in the long run, like in the long run, over many repetitions, I'm going to have values that center on 0 and have a standard deviation of 1. So this is what, this is like if you're learning about central tendency in your intro undergrad stats, this is what they're talking about, right? That you've got in the long run a distribution that's going to have these properties, even though any one of the values that you might pluck out at any one time is going to be anywhere in that distribution, most of them clustered in the middle.
Clustered around. Yeah, no, it's I think a nice example for the when we introduce our students to something like the law of large numbers, right? Because we can keep on making these grow as long as we want. I just don't want R to like give me a kind of collapse. And of course, the larger, the bigger this thing, the closer these numbers are going to be to what you expect to be the theoretical mean. And,
right, as we sort of asymptotically approach infinity, right?
And
so,
and just to sorry, and no, just to say, like, if we were to like do something like slightly different and say, oh, but like I'm bored with the normal, I want something fancier, then it's like, oh, chi-square, and it's skewed, and in this one, we just have to remember that the mean of the chi-square is degrees of freedom. So if I'm asking the chi-square value to have 1 degree of freedom, this value has to be closer to 1. But just highlighting R's capabilities, literally, like in this day and age, you can simulate almost any of the known distributions.
And you've just put 2 here, right? You've got R norm and R chi-square, but there's a whole bunch of different ones that covering all of the major distributions that people are concerned with, certainly in social sciences.
And
just to clarify, just clarifying the, you've got a ggplot statement for those of us not familiar with the ggplot package for making plots. We're not going to go through this thoroughly, but really you've just asked for a histogram with certain color properties and attached one of the built-in themes, so the background looks a certain way.
So I mean, but as you said, like if we were to like remove these and then just like say like, okay, so give me just like the default, we should still be able to get like a histogram. I just once again, Oscar liking the color blue because I like the color blue.
I have my preferences as well. Okay. So we're all on the same page so far. We can draw numbers, right?
Exactly.
We can draw 1,000 numbers or whatever. What's next?
Now, the next one, I think this one makes a lot of sense for people who are a little more familiar with the psychometrics and classical test theory. Like it always gets introduced, right, with this kind of like a little bit crazy idea, right, of like, what would happen if like I could give Andrea a test and she would reply to the test, and then like I have some power, like that thing from like Men in Black, the first one that deletes your memory, and then I give you the test again. And of course, like if the the assumption or like what the model is predicated on is this idea that, you know, you kind of have something intrinsic on you, like your latent trait, your ability that has some value, but there's a variability around that value that comes from the error. Now, I think this can be very beautifully exemplified through simulation, because of course we will never be in the type of universe where we can go around, you know, deleting people's memories and giving them tests over and over again. But we can say like, okay, you know, we can start with, again, you know, just trying to be very explicit. I'm going to create a vector or a place where I can store my result, the results that I'm interested in. I mean, I just call it double. And the thing that this is going to do, it's going to give me just a vector of zeros. There's a variety of ways. People sometimes like to store this as lists. Sometimes people like to store this as matrices. Like, I guess everybody chooses something differently. All I want is like, I need something that has like a little zero or like a little space for everything that I want to store.
Yeah, I've seen that as like asking for a data frame with null, like the null statement.
Oh yeah,
exactly. What is double? What is the double command?
So the double command is just because it's a type of variable, right? Like you have like strings, you have like numerics, and you have like doubles, which is sort of like a kind of number. The only reason if I use double is because it's very flexible. Like if I wanted to store like characters, you know, like actual like words or symbols as opposed to numbers, like you can store them. It's not going to give you I don't know what I'm doing. But yeah, like, you know, you could use something else. I guess like over the years, I've just gotten used to use that one. But as you said, you know, ask for an empty data frame, ask for an empty matrix, and ask for something empty.
Like you can do like data frame where you just say null, and then you tell it n rows and n columns, right? You can just sort of define, in this case, you just have one vector. So that's like a one column, many row data matrix. So you've got lots of options. Okay, so that's something new I learned today.
So we store, we have the thing to store our results. And what we're saying here is like, okay, we're using a for loop. I find them very intuitive, and if you need to do something quick,
I like it too.
So, but I realize that, you know, when you get more involved in simulations, like for loops become very inefficient. And
well, that's those people aren't watching this video, right?
Exactly. Yeah, no, that's a good point. But for our purpose, like if you say, well, okay, what is this for loop doing? You're like, well, I'm just telling it for some variable, like I'm calling I, some counter, going from 1 to 8,000, note that there's like a match between these two. Probably like as we'll see soon, like this could become like a variable. So if you want to do more replications, you'll have to like manually change them. In this case, I just fix it at 1,000. So basically for 1,000 times, I want you to create sort of like store this 10. We're calling this the true score, whatever, like some test and whatnot in this variable called t. And the interesting part here is the error. If we remember from classical test theory, the errors are assumed to be normally distributed with a mean of 0 and a standard deviation that's usually non-zero, because that's what's going to create the error variance from which we need to obtain reliability. So here I just gave it 5 because, I don't know, 5 is nice.
I don't know, we just make up our numbers,
Exactly. And here's where the actual classical test theory model is present, right? X equals t plus e. The observed score is equals the true value plus some error. And what this is doing here is, of course, the square brackets tell the index of where you're going to store things. So if I do x1, it's like, like I didn't
call that one up.
Exactly. If I do x1 here, it's going to be a 0. If I do x2 is 0, x3 is 0, because of course this x only has zeros.
Right.
And basically this would be the whole answer the item, delete your memory. Answer the item, delete your memory. Because of course the for loop means it's going to tell like, okay, simulate, give me a new random, normally distributed random variable with mean 0 standard deviation of 5, add it to the 10, and store it, and then move to the next step. Give me a new one, add it to the 10, and store it, and do these.
So the for statement is asking you to run the commands inside the curly brackets, and then repeat them for as many values of I as you have asked for.
Exactly.
Right. You have for I in 1 to 1,000, so that means it's going to start at 1 and go to 1,000. But you could have had it for I in 5 to 6, and then it would just do it twice. It would start at a counter of 5 and go until it gets to 6. Right. So that's entirely up to you. But this is a pretty common format. It's just asking for a loop to repeat over, right? Repeat and repeat. And anytime you have to repeat anything, whether it's simulation or otherwise, there's often repeating tasks you want to do. Sometimes like some kind of loop like this in any programming language can be really handy.
Oh yeah, no, it becomes like for and while loops, I think, are the most intuitive ones for people to understand. But for loops in particular, because it's I guess like it has this nice like, okay, from this until that happens, do this.
Yeah,
right. Like it's kind of like this has this like, okay, I could see myself, until somebody tells you stop, just keep on doing it.
Yeah.
And
SaaS users. If you're a SaaS user, this is similar to the macro function.
Oh, the macro, yeah, right? Definitely.
Yeah.
And with this one, I guess like just as a sort of like side note of interesting technical things to keep in mind is because every time that there's a for loop or there's I'm asking the computer to do something, the draws from the normal distribution are independent. That independence part is sort of like what creates the model of classical test theory, because if there were relationships between like, oh, every time I ask Andrea, like the error changes slightly or the true score changes slightly, well, now we're not talking about classical test theory anymore. It's this idea that the draws are independent is sort of like what powers a lot of the Monte Carlo simulation. And if I were to ask R to do everything, it's just like, oh, so in I guess classical psychometrics, we call this the propensity distribution, right? Like kind of scores one person. Remember, this is just what we simulated for one person, and these delete your memory, give you the test, delete the memory, give you the test. And the propensity distribution is normal, which is the shape given by the error, and it's centered at the true score, which is defined as the expected value of this constant repetition of experiments. And like I think that just this idea of simulation is, as we were talking about before, is just like you keep on doing it over and over and over again. You kind of bring those classical frequentist ideas. And then you end up with sort of like how the model, the classical test theory in this case, would, predict the data to look like. So we know we're good. We know we're doing something right here.
Yeah, you've got such a wide range of values because you asked for a pretty large error, right? You asked for an error with a standard deviation of 5.
Of 5, right? Exactly.
So this would look different if you had picked a much smaller standard deviation. And if you're simulating your own data ideally you're going to have some sense of how much variability you're going to want around different parameters that are of interest to you.
Like, let's say, like if we were to do it like with one, that's actually not it's the magic of simulation. We could say like, oh, let's see how the data
literally
changes.
Do it again. Yeah.
Like, oh, wow.
It's like really different now. But it's still centered on 10. You just have the extreme values are much less extreme.
Yeah, everything is somewhere between like 7 and 13 or 14. But still bell shaped, still like it's because I always tell people when I'm kind of doing a little bit of demo simulations, simulations are very useful to see whether or not you kind of get what you're doing. Right? Like I get it to the point that, okay, I don't really understand a model or an approach unless I can simulate it, because that means I have an understanding of how the data should look like as it comes out from this model.
Right.
And we learned about the chi-square here. Maybe like, in the future, like one can easily just change these to say like, well, what happens if the error is skewed as opposed to or by model? But of course, that would be probably for a different session. Right.
Well, or for self-study, for those of you that are interested in dipping your toes in, getting your feet wet, you can play around with this, because we'll also, I guess, post this code online so that you can play around with it a bit. Okay, so you've got, next thing you've got is power of a t-test. So everybody should know what a t-test is, right?
We hope so. We're assuming like intro stats knowledge here. And I think this is where we sort of like converge on that conversation that we had. When was it? Like last week, a few weeks ago? Like, remember, was this from like common thread on Twitter about like power analysis? Is it worth it? Is it not worth it?
Yeah.
Like, how do we do it? And this is kind of like what got to this, like, okay, this is a little bit more involved, but I think like if we walk through the processes, we'll be like, oh, this is much more simpler than it seems. Like, I'm just keeping this as a reference because, of course, we live and die by the master Cohen when it comes to power, and this is what most people think about when we think of power. If we're talking about a Cohen's D, we say that it's the small is 0.2, medium is 0.5, and large effect size is 0.8.
Yeah.
So the first thing we're doing here is setting up the number of replications. I'm doing this at 10,000. Like when I was doing it here, it was 1,000, and I'm giving a bit more flexibility. It's probably a good thing to get started is like just saving things as variables, right? So you only have to change the variables as opposed to going through your code, changing every single
numbers.
one.
Yeah,
exactly. And we're also doing a vector, creating an object to store our results. In this case, I'm calling it p-vals because power in this case, we're going to rely on the p-value to be able to get an empirical sense for it. We have our for loop. So this is what's telling me like, oh, okay, for 1 until reps, where reps is 10,000, for 10,000 times, we're going to do something. And what are we doing 10,000 times? Well, 10,000 times what we're doing is we're simulating data for 2 groups. It's normally distributed, has a sample size of 100. One group has a mean of 0 and a standard deviation of 1, and the other one has a mean of 0.2 and a standard deviation of 1. Now, the reason of why I did this, and Andrew, you can tell me whether this makes sense or not. When we talk in terms of power analysis, most of the time we talk about effect sizes, right? We don't talk in terms of the actual raw differences. So, which means there's a little of algebra that needs to be done so that you're simulating the thing that you want in the population. Now, the effects Cohen's D is like a mean difference divided by the pool standard deviation.
Right.
So, but because it's in terms of like a mean difference and a pool standard deviation, it doesn't matter that much what these values are as long as I get the right effect size that I wish to simulate and I'm satisfying the assumptions of the test, which is the other big one.
So here you're just on basically a standardized scale, simulating a Cohen's D of 0.2. But if you want to, you can change those values to whatever would suit your personal t-test. But yeah, so this makes sense to me.
Like I could easily say, okay, this is 1,000 and this is 1,000.2. What? Because the difference between 1,000 and 1,000.2 is 0.2. So I said, let's make life easier and then just rely on the difference. And the pooled standard deviation in this case, because of how I chose the standard deviations, it ends up being the same of 1. And what this is doing, just to sort of like highlight what one replication would look like, is like, okay, I'm creating data for my 2 groups, and I'm asking it to do the t-test. Now, this is something that I made a mistake before when I was getting this code ready, which is that in R, the default t-test is the Welch's t-test, the unequal variances. And I want just the easy, cheesy, vanilla standard t-test, so I need to remind myself to tell them the variances equals true.
Exactly, yeah.
And it does this t-test on simulated data. It gives me, in this case, it's statistically significant. It's catching on this difference. And when you give it this command with this $sign to the actual function, what it's going to give you is the p-value.
Right.
Because I don't care about the t-statistic. I mean, I could care about it if I wanted to see like the sampling distribution of the t. I don't care about the degrees of freedom. All I care about is the p-value. So something that that I'm slowly learning that R is capable of is essentially like reaching into output and extracting individual things you want. So you could have extracted
with a slightly different request, you could probably have also gotten the T, or you could have gotten the confidence interval, or anything else. And it varies how you might what you might ask for depending on the test that you're after. But this is just a literal example of R reaching in and plucking out the value of interest so that you can store that as its own quantity in some other vector.
Like it doesn't always work. It depends on how the person who coded the function initially stored things. But for instance, if I do on class T test, it tells me, if I do $ statistic, it's going to give me the T statistic. If I do $ parameter, it's going to give me the degrees of freedom or the p-value of the confidence interval. So
exactly,
the on class and the str functions are like very useful when you're working in simulation, because you're like, okay, I have this little box of things, and I need to know in which one of the kind of like what part of the box I need to kind of grab my toy, my goodie. In this case, my goodie is the p-value. And so, what I want is 10,000 replications. I want 10,000 p-values coming from hypothetically doing 10,000 t-tests. Which would be sort of the gist of these. So for instance,
let's run it.
I ask R to do it, and you're like, oh, it's doing it, it's thinking, and it finished. If you were to say p-vals, oh, wow, they're all numbers between 0 and 1, as I would expect. If I were to do something like histogram of the p-vals, just as a quick check, oh, okay. I mean, for people who work on replication and replicability, you've seen this before, right? That the sampling distribution of the p-value is very skewed when you have true alternative hypothesis, as in this case. So we know that we're on the right side, doing things the right way. And finally, to get the empirical power, what we're telling R is the following. This is the one that maybe gets a little bit more. So I have this function, this new vector p-vals, which has all my p-values. I'm asking, give me the p-values that are less than 0.05. And I'm going to end up with something that looks like a logical vector of truths and falses, right?
Okay.
Like R is checking the condition. Is this less than 0.05? Yes, true. Is this less than 0.05? Yes, true. And eventually, oh, this is not less than 0.05, so this is false. Now, R stores true and falses as zeros and ones.
Yeah. Okay.
So if you add all the elements of that vector, you get how many out of the 10,000 are actually less than 0.05.
Right.
And to get the actual empirical power, well, what is the out of all my replications, right? The proportion of values that would be less than 0.05 would be like, 0.2926, which already tells me like, so this is the power of my test under the assumptions of a small effect size, normally distributed variables, equal variances, equal groups. I mean, it just gets very, very specific.
Right. So
and
I've got
small effect size. I have this power.
If I have a sample of is it a sample of 100 or is it a sample of 200?
Well, the total sample would be 200, right? You have group one has 100 people, group two has 100 people, so the pool group number would be 200 people.
Okay.
Yeah.
And you say empirical power as opposed to what, theoretical power or?
The theoretical, the analytical, that's the one that our friends on power.t-test from the power package that we loaded earlier on are going to help us out with. Because like if for people who are more familiar with maybe G-power or like the standard calculators to get power, it's going to ask you for the same ingredients, right? Like, okay, it's power of the t-test. So this is already assuming normally distributed variables because the standard version of the t-test assumes that your data comes from a normal population. The sample size is 100, like we did here, because it's taking the per group sample. The Cohen's effect size is 0.2, which is what we're getting here as well. The significant level is, our God-given 0.05, because let's be honest, we're gonna, that thing's going to stick around until we die, which we have right here. And because we are, I'm kidding here, but I always say like, oh my God, like So this is the two sample. Oh yeah, because we have the one sample t-test, right? But in this case, we have two different groups.
Yeah. So that's like an independent samples t-test.
Independent samples
t-test.
We
would call it in psych. Yeah.
And I always tell people, because we're not savages, we're using the two sides. None of that one-sided.
No one-sided test.
No one-sided test. It's like, no, of course I'm kidding. Like we like there's like God loves equally the one-sided and the two-sided. They have different purposes, but let's be honest. We're all thinking two-sided here. Come on, don't at me. You know you're thinking two-sided. And so you asked him like, well, give me the power under these conditions. And you're like, oh, 0.9. So this would be my true power. Like if all the assumptions are correctly done and you sort of like work through the, all the integrals, all the math, all the fanciness, this is the power that should come out with. And as we can see, it's reasonably close, right? It's reasonably close to what we got from our simulation.
Right.
It doesn't have to be all the time, but at least in this case, it's reasonably close.
Now, if you were to rerun the four statements and do this again, would you get the exact same thing?
Not unless you set out the same seed, right? I mean, we haven't had the chance because this is a very quick intro, but like in this case, there should be some variability.
So what happens when you do it a second time?
For instance, 2926, this is 0.2925. So like, for instance, if we were to run, let's do fewer replications just to highlight the uncertainty. Like if we were to do 1,000 replications, notice our DSV is that all that we changed here was the number of replications. It's like, oh, now my empirical power is 0.28, and now there's sort of like this 0.01 difference between the true expected power and this empirical approximation. Now,
so if you wanted to repeat the exact same replication, like if you wanted to generate the exact same 1,000 values again, it would just be a matter of set.seed and run that at the beginning.
1, 2, 3. Exactly.
Anything, like any number in there, So then you would get the same thing over and over again. So for reproducibility, we would generally recommend that you do that.
Exactly, and you can see if I do these, it doesn't matter how many times I run it.
Stay exactly the same.
Always going to be the same. So this is a good observation. Thank you, Andrea. Like in case anybody's like, well, why am I not getting the same answers he's getting? Well, we need to be using the same seed and a host of other things that we won't have time to get today. But it does get at least to this idea that, this is kind of how you would do power under an empirical setting. And this is just my check to see here's my two groups kind of look
basically
like that.
The same.
Exactly.
So, so just to kind of wrap it up here, because we're just about out of time. Basically what we've shown here is that the kind of core of simulation is asking a computer to draw a bunch of values from some predefined distribution, and to do that in a pseudo-random way, right? Random being how the random number generator in the computer is functioning. And that we can use that facility of a computer to construct distributions of things that have the properties that we want, that group differences that are the size we want. And ultimately, if you're trying to construct a simulation of something a little more complicated that doesn't have a prepackaged analytical solution like a two-sample t-test, you can use this basic technique to kind of scale up to getting a parameter in a latent variable model, for example.
Anything complicated.
Starting with drawing many independent observations. So that's what is going on when we're talking about simulating. So Oscar, thank you so much for putting this code together.
No, that's perfectly okay. It's always a pleasure, and we'll talk more in our next episode then.
Yeah, thanks, and hope you enjoyed this. We'll see you next time.
Perfect. Thank you. Have an excellent day.
Bye.
Bye.